Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to talk about estimating the standard deviation or variance. Recall that for a population, standard deviation is denoted by sigma, and the variance is sigma squared. For a sample, the sample standard deviation is S, and the sample variance is S squared. The statistic that we use for variance is chi-squared. The chi-square statistic also has degrees of freedom, just like the t statistic, and it too is sample size minus 1. We use this for normally distributed populations, with variance equal to sigma squared. The distributions are skewed right in this way. The chi-square curve originates at the origin. So a left tail chi-square on the left will be very distinct from a right-tailed chi-square on the right. There's a table in your text that you can use for finding these critical chi-squares. Table A4 on page 735. And this table gives only right-tailed chi-squares, areas to the right of the chi-square value that is given. Excel allows you to give the area and it will tell you the chi-square. The command is chi-sq.inv for the inverse chi-square. This command gives only left-tailed chi-squares, only the values over here. Yet there is a command that will give you right-tailed. You can use chi-square inverse.rt. for the right-tailed chi-square. If that's not confusing enough, OpenOffice uses chi-inverse, and it gives you right-tailed chi-inverses. The TI-84 under the distribution button, second distribution, has a chi-square CDF, and if you select that, it allows you to specify lower and upper values. And so you can specify here and here, or here and here. So you can choose whether you wish to have upper or lower values for the areas that you get. It doesn't allow you to specify the area and give you the critical chi-squares that we will be needing. Now, since chi-square, yes, this is the Greek letter chi, is n minus 1 s squared over sigma squared, we can solve for sigma squared as n minus 1 s squared divided by chi squared. You just multiply both sides by sigma squared and then divide both sides by chi squared to obtain this. We find confidence intervals for the variance as follows. We'll have n minus 1 s squared over chi squared left, and then n minus 1 s squared over chi squared right. Yes, the right and left are on opposite sides. The right chi squared is bigger than the left chi squared, and when you divide by bigger numbers, you get smaller values. So the larger value will be dividing by chi squared left, the critical chi-square on the left, and the lower limit for the confidence interval is found by dividing by the larger value, the chi-square, critical chi-square on the right. It follows immediately that a confidence interval for the standard deviation is obtained simply by taking the square root. As per usual, we'll round to 1 decimal place more than in the data. Again, the population must be normal. This is more important here than for means. And the sample must be random. I'm going to write down some data for pulse rates, and then we're going to find a 95% confidence interval. For the standard deviation. The pulse rates are 76, 76, 84, 74, 66, 62, 78, 68, 62, 62, these must be athletes, 74, 80, 54, 74, 74, 84, 60, 52, 84, 66, 56, and 66. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So we have n equals 22, which gives us the degrees of freedom equal to 21. I'm going to enter this data as a list on my calculator and have it calculate the standard deviation from the list. To make the list, I'll press Stat and then Edit. And then I'll just type in the numbers: 76, 76, 84, 74, 66, 62, 78, 68, 62, 62, 74, 80, 54, 74, 74, 84, 60, 52, 84, 66, 56, and then 66. Second quit. Stat. I want to calculate, so move over to the calculate column, and one variable statistics from list 1. Now it gives me two different standard deviations, Sx and sigma x. Sigma x would be calculating the standard deviation for populations, whereas Sx is the standard deviation for samples. We're getting 9.77-ish. We'll round it to that point there. The first step is to do a normal quantile plot. To check that the data comes from a normal population. To do this, since we have n equals 22 data points, we need to find the z-scores corresponding to 1 over 44, 3 over 44, 5 over 44, and so on, all the way up to 43 over 44, a whole bunch of these, and find their corresponding z-scores. We'll sort the data from lowest to highest, and then assign these z-scores, and then plot the normal quantile plot. When you do that, you'll find that the data end up looking something like this, and in fact it is well represented by a straight line, and so the data will come from a normal population. I'm going to enter the data that we have from our list into a spreadsheet. So I'm going to have 76, 76, 84, 74, 66, 62, 78, 68, 62, 62, 74, and then 80, 54, 74, 74, 84, 60, 52, 84, 66, 56, and 66. Scrolling that into view, we have all of these data values. We should sort the data. So I'm going to put these in rows and sort. I'll type this 1, 3, 5 and see if this can carry that pattern all the way to the end of the list right here. We need to divide each of those by 44. And so we'll drag that formula down here. And we'll use the norm inverse function with a mean of 0 and a standard deviation of 1. And we'll paste that down at the end of the list here, giving us all of those z-scores that we need for the normal quantile plot. We'll select the first column and this last column. I'll press the Control button
so that I can select both. We'll insert the chart, but we'll have to select the kind of chart that we need. The XY scatter chart is the kind that we need. And you can see then that the data does seem to lie more or less along a straight line pattern here. Let me move the chart more into view.
Now, to get the critical chi-squares, I'll use table A4 on page 735. The confidence level is 95%, so alpha is 0.05. We need to split that between the two tails. Alpha over 2 here, and alpha over 2 here. The table only gives you right tails, so we're going to look up 0.025 for the right-tailed. With the degrees of freedom equal to 21. We go degrees of freedom down the left column, and across the top row we have 0.025, and we're getting 35.479. To get the left chi-square, we have to leave 2.5% on the left. The table only gives right, so we have to use an area of 97.5% or 0.975 in order to figure out this left tail. We'll have 97.5% of the area here, 2.5% here. So 97.5, that's the third column with 21. We get a critical chi-square of 10.283. It follows then that the standard deviation is bounded above here by, let's see, we have degrees of freedom 21 times s squared divided by the chi-square left, and the other side we'll have 21 9.77 squared divided by 35.479. We can crunch these numbers on our calculator. We'll have square root 21 times 9.77 squared divided by 10.283. That's 13.9. Well, I guess that rounds to 14.0 because it was 13.96. On the other side, square root 21 times 9.77 squared divided by 35.479. And that gives us about 7.5, rounding to 1 decimal place more than was in the data. The data was given to us as integers, so we can use 1 decimal place in representation for our interval here.
We can calculate the standard deviation in the following way. We can just take the standard deviation of the prior list all the way up to number 1. Giving us the standard deviation that we had before. We need the critical chi-squares. So we have to enter the area 0.025 and the number of degrees of freedom. And we delimit these by semicolons. So you can see we get one of our critical chi-squares. For the other one, the area 0.975 with 21 degrees of freedom. So we can get the critical chi-squares using the chi-inverse in OpenOffice that I'm using here. The standard deviation from the STDEV command here. Show you the commands one more time.
We can use the formulas that we've derived to determine sample sizes. To understand our notion of margin of error here, note that our intervals are of the form given by this sequence of inequalities. So we have this left endpoint and a right endpoint. The margin of error is going to be halfway the distance across this interval. So we have to define it in the following way. We'll take the bigger of the two values and subtract the smaller of the two. That's the distance across the interval. And multiply by a half to get half the distance across. We can factor the common numerator out of this expression. We'll have the square root of n minus 1. The square root of s squared is s. All that's left inside of the brackets here is the square root, 1 over the square root of chi left squared minus 1 over the square root of chi right squared. Given the margin of error, we can now solve this equation for n. The easiest thing to do is to multiply both sides by 2, divide both sides by s. We'll divide this in the braces here into the denominator. We'll get n equals 1 plus, we'll have squared everything else. Yielding our estimate for the sample size required. We can either use the table for finding the critical chi-squares, or we can use a computer. The calculator doesn't have the inverse chi-square needed to find the critical chi-squares.